and the tubes fire off. Video is now released. Okay, video is now released after mute is released, and it comes up to the cable here at 8-bit LVDS feed, and video now arrives at the TCON board for distribution from the TFT control board, TCON, distributed through 2 cables which are hidden by the shield to the TCON, to the TFT panel. So now you have the entire turn-on sequence and what to look for right in a nutshell by looking at the back panel. So knowing that, we can proceed. Let's look at a close-up of pulling the boards out. This just shows you what to disconnect the cables. Remember the communication to the main board? That's the cable to the main board. This is the cable to the AC input. This is the cable to the vacation switch. And these are the 2 cables to the backlights. There's that primary side fuse. Maybe I should draw a circle around it. It's better. Yeah. Fuse, your bridge rectifier that you see there, the ballast FETs, the ballast test point, which I'll show you closer later, sequence in a graphics form. And it does start just like I said. Step 1, you apply AC power. Step 2, you send 5-volt standby down to the main board. And at that time, now the main board, step 3, changes the voltage into usable voltage for the microprocessor. Okay, 1 is B+, which is a 3.3 volts. They call that, by the way, 3.3 BCM, and because that stands for Broadcom module, which is the video processing generation, but this is also the microprocessor in this TV. And then the microprocessor is ready to go and it's fired up. It's communicating to the front control board. It's waiting on IR commands, which is an IR receiver port or the power button. And if you press the power button, then you generate the first command out of the microprocessor called power on. Labeled on the schematic as relay on, by the way. And that turns on some other circuits on the main board, but the bottom line for you is it outputs a signal to the power supply, which turns on the 224 volts, and the regulator circuit, which fires off the 105 volts for the ballast. So I think I ought to make that a little clearer about what's happening there. Let me put me a little note. All right, very good. Oh, okay. So that fires off the regulator, but the ballast, as you noted, this time is not turned on. Okay, then the next command that comes out of the microprocessor is LVDS 12-volt panel control. And the panel control then fires off 12 volts up to the TCON board. Notice that that's the same 12 volts that's coming from the power supply. That's critical, I think, to remember. And then finally, the inverter on command is generated, and it arrives at the power supply. It really doesn't do a thing for the power supply. It just simply hits the ballast control IC and tells it to start generating the 64 kilohertz signals at 1.2 kV to drive the bulbs, and the bulbs illuminate. Now, we need to introduce you to some new terms, and that is ADIM and PDIM. ADIM and PDIM. If you look, you have ADIM and PDIM that are fed up from the video processing portion of IC100. Now, here's something interesting about this. We've been using ADIM and PDIM for a long time, but you might not be aware of it. I want you to be aware of it like this. ADIM is not ever used. We simply fix it to a specific voltage. Now listen, there's even a port out of the microprocessor that's called ADIM, but they fix it through software to not move. So that's a good thing. It's fixed. But the PDIM we do use on a lot of our sets, most all of them with LCD backlights. That stands for PWM dimming, pulse width modulated dimming, or it may be also called DIM for digital dimming. It may also be called PWM DIM, so I just want you to know, and some rare occasions it'll be called BR2, but that's rare. Now here's the thing about this. Let me give it to you in general terms first. In general terms, the digital dimming is responsible for global dimming. Global, meaning everything goes down in dimming at one time. Now what are we dimming? We're dimming the backlights. How are we dimming it? I'll show you in more detail shortly. But let me give you the bottom line. They drive the bulbs with a 64 kilohertz, let me say it clearer, 64 kilohertz signal. And that 64 kilohertz signal, think of it as a given time frame, the number of pulses in a given time frame. The more we pulse the bulbs in a given time frame, the brighter they are. And the less number of pulses we pulse it in a given amount of time, the dimmer they are. So by a DC voltage that can usually vary between 0.3 volts and it can vary up to approximately 3.4 volts in every one of our sets, we can affect global dimming. 3.4 volts is the brightest the backlights can be, and 0.3 volts are the dimmest that they can be. They don't ever actually go out or go off completely. That would be kind of silly, but they do get very, very dim. Now, there's a reason I'm telling you all this about global dimming command, PWM, DIM, and that's because I want you to know that it can be affected by several different things, or the voltage level can be affected by several different things. Let's take note the most common thing and what is called the maximum threshold level. The customer has access to the service, not service, but customer's menu. They hit the menu button, they select picture, and one of the selections in the picture menu is backlights. And they have a choice in the backlight settings of between 0% up to 100%. They can set the backlight settings. That's actually a customer's adjustment. And let me give you an example. Let's say the customer put it, this is not exactly dead on the money, but it's close enough for you to get the understanding, at 50%. So at 50%, the voltage is roughly 1.8 volts. Well, that is the maximum that any other effect on the backlights can have. So that's why they call it the threshold. If you drop the top threshold, every other adjustment effect will go down accordingly. Now, in this television, the only thing we deal with manipulating PDIM is the customer's backlight setting and the picture contrast ratio. The contrast ratio is measuring the distance between the brightest white and the dimmest or the blackest black. The difference between the brightest white and the blackest black is the contrast ratio. Now, let me give you an example of what I mean by this in relationship to the backlights. A picture, you're having a polar bear fight at 12 noon in the North Pole. You can understand that is very bright, a lot of white, and very little contrast ratio. So the backlights are really, really bright. Now a penguin walks in as referee. Well, the penguin, the black feathers on the penguin represents the black floor of the video. So now we have a contrast ratio that's huge. You have a black floor all the way up to the white peak, sunshiny day, 2 white polar bears in the snow. So now we have a gigantic contrast ratio. So the backlights still remain at really high values, but the deal is we have to shut off the light coming through the area where the penguin is black. Okay? So that's controlled by the panel, the LCD panel. Now imagine that this fight goes on so long that the bears get tired and they decide to go have a beer and walk into the bar that is dimly lit. Now you have the brightest white has dramatically dropped. The black floor, still the penguin's black feathers, it still represents the black floor. It didn't move. It's still black. So what happens was your contrast ratio dramatically dropped the distance between the white maximum and the black minimum. So now the backlights can be dropped because you don't need that super bright backlight since the contrast ratio dropped. Make sense? So the microprocessor, or the BCM chip in this case, which is the micro, monitors the contrast ratio and manipulates the digital dimming command in accordance to the contrast ratio requirement. Customers' menu for backlights manipulates the maximum threshold of which PDM can reach. You need to be aware of that, because what happens if by accident or something goes awry, which we have seen, and you lose continuity between that PDM and the backlight controller, whether it be on a ballast by itself. You understand? If you have a ballast by itself and you have a power supply and you have a main board, this PDM signal must leave the main board, arrive at the power supply, do absolutely nothing on the power supply except get routed right over to the ballast. Then the ballast backlight control, the ballast driver IC, receives that command, which is nothing but a fluctuating DC voltage, and it knows how many times to drive the backlights within a given time period with its particular pulse width. Bingo. You lose continuity, you can drop the backlights very dim and think you have a ballast problem. Think you have a power supply problem, when the problem is you've lost your PDM signal. How about this? Some customer and or kid and or somebody, prankster, has been in the customer's menu and dropped the backlights to 0 and didn't tell anybody. Backlights are very dim. Customer complains about a dark picture, and bingo, the problem is simply a customer's setup. They quickly look at brightness and contrast, and they'll see those at 100%. But what they'll fail to look at is the backlight setting. And then finally, this BCM chip on a lot of TVs, not this one specifically because it's a smaller version, and the reason it's smaller because it's only dealing with 8-bit LVDS feed up to the T-Con. But when you got those that actually have true motion, that are dealing with 24-bit arrays running dual LVDS feeds up to the T-Con board, they run really hot. In fact, those are metal back flat pack chips. And what happens is sometimes they can cause the board to separate around the chip, and you start having fluctuations on PDM, and the backlights flicker. And again, you think you've got a backlight problem, a ballast problem, a power supply problem, when the whole trouble is that your backlights are flickering because PDM is fluctuating. So spray some coolant spray around the processor, the BCM chip, and if the problem changes or disappears, bingo, you've got a main board failure.